In this demonstration, you'll learn how to simulate a multi-phase flow consisting of air injected into a liquid-filled mixing tank. I will consider a simplified case in which there is no flow into or out of the reactor. This is a reasonable representation of the initial conditions in a real reactor at the start of a new process. For this simulation, I will determine the reactor's quality of mixing and power requirements. At this point, I've loaded the reactor's mesh into ANSYS Fluent. Let's start by reviewing the reactor's geometry and boundary conditions before setting up the multi-phase model. The geometry of this three-dimensional model represents an experimental lab reactor which comprises a Rushton blade turbine, a pitch blade turbine, a ring sparger, and 4 thin baffles. Note that since the aspect ratio of the tank significantly exceeds the normal value, 2 impellers are required for good mixing. The Rushton blade turbine's primary purpose is to disperse the introduced gas by providing shear. The pitch blade turbine mixes the bulk fluid by simultaneously pumping and shearing. Air is injected at the center through a ring sparger surface. The inlet's geometry ignores the presence of small inlet holes, and instead, the inlet is approximated as a uniform circular strip. Finally, baffles located on the sides of the tank prevent vortex formation. The boundary conditions for the reactor are as follows. The bottom and the side walls are defined as no-slip walls. The top of the fluid, in reality, is open to the air. The corresponding boundary in the simulation is modeled as an outlet with a degassing condition, allowing for air bubble release, which facilitates the application of the Eulerian multi-phase model. Now to set up the simulation. First, I need to specify the operating conditions. In this case, competition between opposing gravitational and buoyant forces influences the movement of produced air bubbles. To account for this, I will include gravitational acceleration and set an operating density equal to that of air. Note that for multi-phase flows, the operating density should be set to the density of the least dense phase. This warning message isn't cause for alarm. The degassing boundary condition, which was defined within the mesh, is not appropriate for the given set of models. I can fix this by adding the multi-phase model. Since the 2 phases, gaseous air and liquid water, aren't in equilibrium throughout the simulation, the Eulerian model must be used. Once I activate the Eulerian model, 2 phase descriptions become available in the phases sub-branch. I will describe the primary phase, which is the bulk fluid, as liquid water. The secondary phase is gaseous air. When the air enters the reactor, bubbles are formed. The size of these bubbles, which is related to the size of the inlet holes in the real reactor, is entered here. In this example, the hole diameter is 1 mm, so I will assume a bubble diameter of 1.5 mm. Within the Phase Interactions menu, interactions between each phase can be described. In this example, drag between air bubbles and the bulk fluid is best described by the Grace model, which applies well to liquid-gas mixtures with low gas density and bubble sizes of 1 to 2 mm. I must also include a value describing the surface tension of the bubbles. Many different phase interactions, such as lift, wall lubrication, turbulent dispersion, and turbulence interaction, could be described here. However, for this case, only drag needs to be considered. Mixing in this reactor occurs primarily through turbulent fluctuations, so naturally I must add a turbulence model to the simulation. In this case, the standard K-epsilon model will do. Since the volume fraction of air in the bulk fluid is very small, I will use the dispersed multi-phase turbulence model. The dispersed model assumes that turbulence in the primary phase dominates, and the turbulent behavior of the secondary phase is approximated from the mean characteristics of the primary phase. Using these model settings, I could run a multi-reference frame simulation, which provides steady-state data, or a moving mesh simulation, which provides transient data. For my analysis, I only need steady-state data, so I will set up the computationally less expensive multi-reference frame, or MRF simulation. The key to setting up a MRF simulation lies in the specification of cell zones. This is where the motion of each component within each reference frame is defined. Below, you'll notice that 3 cell zones are listed. This cell zone contains the Rushton blade impeller, which is set to rotate at 450 RPM in the absolute reference frame about the z-axis. Likewise, the second cell zone contains the pitched blade impeller, which is also set to rotate at 450 RPM in the absolute reference frame about the same axis. The final cell zone comprises the rest of the tank, which is stationary in the absolute reference frame. Any boundary condition located within a particular cell zone uses the same reference frame as the cell zone. This is why the wall boundary condition for each impeller is stationary. When the multiphase model is specified, options controlling the initial velocity and volume fraction of each phase entering the inlet become available. Since I am using the dispersed turbulence model, I only need to set turbulence specifications for water. In this case, exclusively air will be entering the inlet, which is reflected by my volume fraction setting. The calculation is now ready for submission to the solver. The solver will use the coupled scheme, and the run is pseudo-transient. I will use an automatic time step method with a timescale factor of 1. The solution should converge after 850 iterations. After 850 iterations, the convergence of the solution is satisfactory. Let's take a look at the produced flow field. Shown is a contour map describing the volume fraction of air on the XZ plane. This plot shows how the air travels up the mixing tank as it interacts with each impeller. When I change the viewer to look at the XY plane, I can see that the air is collecting on the bottom surface of the Rushton blade turbine disc before it's dispersed by the impeller's blades. The shape of the Rushton turbine seems to be creating cavities behind the turbine. Here I have plotted a velocity vector map showing the movement of the water phase throughout the reactor. I can clearly see how the water circulates throughout the tank. Notice that the water forms a closed loop since it cannot escape the tank. Now I can calculate the torque about the shaft for the Rushton blade turbine. In this case, the impeller is rotating counterclockwise about the shaft, which lies on the z-axis, so I will set the moment axis to -z and compute the torque. That seems like a reasonable value. Using this data, I can compute the Rushton blade impeller's power number and compare that value to the empirical model. This concludes this demonstration, showing you how to solve a multi-phase mixing problem using ANSYS Fluent.